Okay. All right. So we've been dealing a lot with lines lately, various ways of writing the equation for a line and solving various problems involving lines. And today we're going to do the same planes. Okay. Okay. So we'll see how we can describe a plane with some kind of equation. Any 3 points that are not collinear can be used to describe a plane. So I'm going to call these points 0, 1, R2. And then we find vectors coming from R1, so coming from R0 as the common initial point. And then we have terminal points R1 and R2. We're going to call these vectors V1 and V2. So these are 2 directions that are contained within this plane. Now, so if I have a vector that is orthogonal to both V1 and V2, any vector that resides within this plane is going to be orthogonal to this vector too, because it can be described as a linear combination of these 2 directions, V1 and V2. So I'm going to call this vector N. So this is the normal vector of the plane. And you could, if you have 3 points in the plane and you define V1 and V2 in this manner, then how can we get N from what we have here? Not quite. Try again. Yes, I guess it's the only option left, developing a product, but yes, okay, cross product of what? V1 and V2. Because N has to, anytime you have a situation where you want one vector that is orthogonal to 2 given vectors, cross product. Now, depending on the particulars, the vector N might be pointing in the opposite direction, might be going down, but the point is it's going to be perpendicular to any vector within the plane. Okay. And that's all we really need. Okay. So now suppose I have some arbitrary point that's somewhere within this plane. So this point over here, I'll just label it R. Okay. Now, if I draw a vector ending at this point from any other point in the plane, and I'll just pick R0. So this vector right here, that vector is R minus R0. All right. And remember, R is any point in the plane. That vector has to be perpendicular or orthogonal to N. Any direction within the plane is. So this leads us to the vector equation of a plane. So it's now we use dot product. And dot product of R minus R0 must be equal to 0. That's how we know that 2 vectors are orthogonal. So N is the normal. R0 is some given point in the plane. So it is a position vector. And then R with no subscript, that is any point in the plane, a generic point. So the plane consists of all vectors R that satisfy this equation. But just as we had parametric equations of a line that tells you x equals this, y equals this, z equals this, it'd be nice to have an equation for a plane that it's written in terms of x, y, and z. That's what we're accustomed to working with. So I'm gonna work with these vectors now in terms of their components. So I have my normal vector n having components a, b, and c, or the x, y, and z components. Our given point in the plane, R0, has components x naught, y naught, z naught. And then R is some generic point that's somewhere in the plane that has components x, y, z. Now substitute all of those into the vector equation of a plane. And what we get is, all right, so if ABC dot product with x minus x naught, y minus y naught, z minus z naught, 0. But then I carry out what the dot product is. So you multiply corresponding components, add them up. Okay. Again. Every time. Okay. So we just talked about this. So here we have an equation of plane involving x, y, and z. But another common way of writing it is this. If I distribute, I have ax plus by, this is equivalent form, plus cz plus d is equal to 0, where d is given by minus n dot product with R0, or in terms of what I have written here, it's equal to minus ax naught minus by naught minus c naught. So most often, like in homework problems and such, a plane will be described using an equation like this. But now we know what the coefficients in the equation mean. So a, b, and c are the components of your normal vector. D is minus dot product of a normal vector with some point in the plane. Any questions about how a plane is described? Okay. I'll work for an example where you're given 3 points. And the goal is to come up with the equation of a plane containing those points. Okay, so the 3 points we have. E naught. 1, 4, 1. 1 is 5, 1, minus 1. 2 is 4, 4, 4. Okay. And we can think of these also as position vectors, in which case I ought to use the angle brackets, but I guess for homework systems, it's too lazy to use them, and so am I. Okay. So R0, R1, R2 are position vectors for those 3 points. Okay. So then I need 2 vectors that lie within the plane. So find V1 to be R1 minus R0. So we have 5, 1, minus 1, minus 1, 4, 1. Three, 2. Okay. So that's one vector that lies in the plane. Then we say V2, that's R2 minus R0. So we subtract these 2. Get 3, 0, 3. Okay. Now what do we do? What's next? Of? Yes. Okay. Okay. Plus. Okay. So n, normal vector n is v1 cross v2. And I like to write it this way, vectors on top of each other. Helps me keep everything straight with what to multiply, what to subtract, and all that. So x component, I have minus 3 times 3 minus, well, there's a 0 here, so it's going to be minus 9 for the x component. For the y component, I have minus 2 times 3, so minus 6. Minus 12, so minus 18. And then for the z component, I have 4 times 0 minus 3 times 3. So minus minus gives me a plus, so I have plus 9. So that is a vector that is normal to the plane. So these are the coefficients A, B, C for the equation of my plane. What's left is I also need the constant D. So D is equal to minus and dot product with R0. So that'd be minus dot product of minus 9 minus 18 plus 9. Dot product with R0, which is 141. We get -9 minus 18 times 4 is minus 72 plus 9. Okay, so the 9's cancel, so we have minus 72. So D is equal to plus 72. So now the equation of this plane is minus 9x minus 18y plus 9z plus 72 equals 0. Any questions about how that equation of a plane was?
Not bad.
What?
Not bad.
Okay, good. All right. I don't remember off the top of my head, but there's probably a problem like this in the final. One thing you can do to check your equation is here we have two other points that are in the plane. So presumably if you plug in any of those points into this equation, it should be satisfied. And at the risk of embarrassment, I'm going to try it right now. So by test, E2. That's 4, 4, 4. Oh yeah, it's gonna work. We have minus 9 times x, which is 4, minus 18 times y, which is 4, and then plus 9 times z, 4 plus 72. So we have minus 9 times 4 and plus 9 times 4. Those will cancel. And then we have 18 times 4, so minus 72 plus 72. So it really does equal 0. Sometimes there are relatively quick things like that you can do to check your answer, which if you have time, like on a test, that might give you an idea, especially if it exposes the wrong answer. But you can hurry to fix it. Which reminds me, I never brought this up on time of our midterm. But what I found is over my 14 years here, not to mention having taught at 3 other universities. And speaking of USM students as a breed, or subspecies, if you will, y'all give up on tests way too quickly. I was really surprised when I first started teaching here, how I give a test that's for 35 minutes or whatever, and people were walking out after 25 minutes or something like that when they're not done. At first I thought, oh, are you showing up and you're done fast? Like, no, they're just giving up. No, I mean, it's like, give yourself a chance. And it's definitely a lot, I can understand having that initial freak out. And then you need time to recover from that. But yeah, it's just an observation. That I know there's tempting to think like, oh, well, I just don't know it. But a lot of it is influenced by your state of mind. If the more stressed out you are, that your brain's not going to be at your best. And if you give yourself some time to search up down, that knowledge that might appear to be gone might actually come to you. And I can tell you that because that has happened with me when I was a student. That at first I don't know what to do. I may move on to something else and then come back to it. It does happen. So give yourself that time. Now, on the flip side of that, when I was at UC Irvine, I did have a student who would always be the first one to walk out of the test, and he wouldn't just walk, he would strut. Like, I finished this test first. Y'all suck. Something like that. It's part of my language. But and I found it interesting because he was always a B student. So it seemed kind of weird, like he was an act or something. I don't know. Go figure. Okay, now this next problem is actually ripped from the homework. Just like Law and Ripstone are ripped from the headlines. Okay. Involving a line and a plane. if you have, a line and a plane that are not parallel to one another, they'll intersect at a point. So find the intersection of the, plane, minus x minus 8y minus 3z equals minus 34. I noticed that in the homework, the way this equation is formatted, it can be a bit hard to read because these coefficients, I guess, were randomly chosen. And it's not smart enough to, like, if it's a 1 to not put it there. So it's like minus 1x minus 8y. It looks kind of weird, but okay, so the intersection of this plane and the line that's given by a vector equation. So vector r, which is a generic point on the line, is equal to this point on the line, 5, plus this direction vector, minus 4 minus 5, 5, times the parameter t. Now, since the equation of a plane deals with x, y, and z, it'd be nice to have that kind of description for the points in the line also. So take this and write it in terms of parametric equations for x, y, and z individually. So what would the parametric equations of this line be?
Minus 14.
Hmm.
-1 minus 5c. 5 plus 5c.
Okay. Okay, so now we have set of all x's, y's, and z's that belong to this line. And we want x, y, and z belong to the plane also. So find out where the line and the plane coincide. Can anyone suggest what I should do with what I have here?
Plug in.
Plug in what into what? Yes, so I substitute x, y, and z into here. Parametric equations for a line into the equation of a plane. So now I have minus x, so it's minus 2 minus 4t, minus 8 times y, which is minus 1 minus 5t, minus 3z, which is 5 plus 5t, and that must equal minus 34. So these are the actual numbers that I got for my version of a homework problem. And I was working out to write up in the notes. And about, these numbers are not gonna work out nicely at all. Then I realized that I'd forgotten one of the minus signs in here. So like, actually, yeah, in this case, things do work out very nicely. So what happens is once you expand out all of this and simplify as much as you can, it all condenses to 29t is equal to minus 29. So the parameter of the intersection point is at t equal to minus 1. So now you take this parameter value and you substitute it into the 3 parametric equations. And you get x is equal to 2, y is equal to 4, b is equal to 0. So this is the this is the final answer. The intersection point. So we're actually two intersection of plane and line problems in the homework. The other one is where the plane was simpler, like where's the line cross like the XY plane? So you just, the equation you're playing in that case is, z equals 0. So you could, so that problem is a bit simpler. But you could use this approach for that too.
Line. That's why I'm finding.
Oh, wait. Oh, no, for the whole line, no. It's just that,
So where they intersect.
yeah, where the intersection is a point in the XY plane. Yeah. Yeah, because the line's going all over the place in Z, and so is the plane. Okay, questions about this one? Okay. So now for a different sort of problem involving planes. Actually, I'll talk about general procedure first. Those are intersecting planes. So if you have two planes that are not parallel, where they cross, the intersection of them is going to be a line. The question is, what is the equation of that line? Okay. All right, just be sure I have this fresh on mind before I proceed. Okay. All right. Now, since the intersection is a line, we need to compute what two things that would describe a line for us. And keep in mind, we're dealing with lines that are in three-dimensional space. So what are, okay, I'll narrow it down. What are two vectors that would completely describe a line?
Would it just be A, B, C, D?
Uh,
Like,
You're thinking about a plane though. Yeah. Right. So, like, so let's, we assume we already have two equations, the equations of two planes that have their respective A, B, C, D. But as for determining what we're gonna do with those equations, like, so for example, in two dimensions, you're familiar with describing a line using, slope and y-intercept, but now we're in three dimensions. So, if you think like vector equation of a line, which has been used so far today, what are two whatever two vectors that make up that equation, what do they mean?
This position R0 R1.
What, okay, well, well, no, what were we saying?
The position vectors R0 and R1.
Well, R0, yes, so we need a position vector, so we need a point on the line. Okay. And what else? So that partly describes the line. What else describes the line? Yes, the direction numbers. So R0 and B. So direction vector, which consists of a direction numbers. Okay. So it's important to see, like, okay, we're looking at an equation of a line or equation of plane. Well, not just the numbers themselves, but what are their meanings?
Other than the fact that we call R0 a position vector.
Yeah.
Other than a direction vector, what's like the difference between the two?
Is it because it's tied to a certain initial point?
Yes, when you have a position vector, the initial point is always 0, 0, 0. Whereas a vector like this, what's not a position vector, we don't really care about what the initial and terminal points are. Like, we can move it around. We care about its magnitude and direction. All right. Okay, so if we can figure out these two things, then we're good to go. So the equations of our two planes. Okay, so let's assume those are A1x plus B1y plus C1z plus D1 is equal to 0 for first plane. A2x plus B2y plus C2z plus D2. 0 is equation of second plane. Okay. Now, to know the easier one of these two things, we need point and line direction vector. The direction vector is the easier one to get. So the normals of the planes are N1, which consists of components A1, B1, C1. And then second plane, we have normal N2, that's A2, B2, C2 as components. Now, the line sits within both planes. Any vector within a plane has to be orthogonal to its normal. Since this line resides within both planes, it must be orthogonal to both normals. So, what is the direction number, direction vector for this line?
The cross product of N1.
Yes, yeah, N1 cross N2. Okay. The line is in both planes. Means it must be perpendicular to both normal vectors. Okay. All right, so the job is part done. We still need the coordinates of a point, any just one point will do. That's in both planes. So you can think of it as finding x, y, and z that would satisfy these two equations. But the thing is, we have three unknowns, X, Y, Z, we only have two equations. So what does that mean, like from a linear algebra standpoint, about how many solutions? Yeah, and of course, we know there are infinitely many solutions. We want there to be infinitely many solutions because it's a line that consists of infinitely many points, but we still have to find one. So how you go about this is a rather haphazard procedure, but it's kind of like the haphazard procedure for finding out whether two lines are, intersect or skew. So what you can do is, right. So if we try setting z equals 0, in other words, we're making the assumption that there's some point on this line that has a z coordinate of 0. And then you would get a1x plus b1y equals minus d1. A2x plus b2y is equal to minus d2, just from rearranging what's left, actually get rid of the z terms. And then you check. Does it have a unique solution? Using what I talked about last time, for instance, you can check if the coefficients are proportional or not. Like is one equation is a scalar multiple of the other. In which case they're not independent. So if not, you can try y equals 0 instead. And see if that gives you two independent equations. Okay. Okay. So then you can, so in this case, we're assuming z equals 0, you solve for x and y. That gives you a point on the line. Okay. Any questions at this point? I'm about to do an example, but. All right, let's do the example already. Okay. All right, so here we want the intersection of these two planes, x plus 3y minus 2z plus 10, 0, and then we have the other plane is 2x minus 4y plus 3z minus 5 is 0. Okay. So now we get the normals. What are the normals of these planes? The first one. Okay, all right, so now that's the n sub 2. Okay, all right, then what?
Find the cross product.
Yes. All right, so cross product n1 and n2 to get our direction vector v. So we have 3 times 3 is 9 minus 8, so we get 1. Okay, then we have minus 2 times 2, so minus 4 minus 3. Then we have minus 4 minus 6. Okay. All right. So we have the direction numbers of our line. The only thing that remains is to get the coordinates of some point within both planes. So finding this solution x, y, and z of this system. I guess if you're feeling extra linear algebra E, and some of you probably sick of linear algebra because you just had a test in it this morning. You could do like row operations on this and find your pivot free variables and so forth, and get a solution that way. And if you really want to do that, that's okay. I'm describing a procedure for those of you who have not had the joy of linear algebra. Okay. So to find point in both planes. All right, so I'm going to try setting z equal to 0. So now we have this system of equations, x plus 3y is equal to -10 from the first plane. And then I have 2x minus 4y is equal to 5 from the second plane. Look at the coefficients, 1, 3 here, 2, -4 here, they're not proportional. Yes, the rows are linearly independent. So another way of putting it is the vector 1, 3 of coefficients from first equation not parallel to coefficients from the second equation, 2, -4. So that means this system does have a unique solution. Okay. I'm not going to go through all the algebra of solving it. So the solution turns out to be x is equal to -5/2. Y is also equal to -5/2. Okay. So the point on the line is given by vector r0, which is as x components -5/2, -5/2, and 0, because we assumed that z equals 0 to get those x and y values. Now I can describe fully the line of intersection. I might have Haphazard board use. R is equal to this vector, 5/2, -5/2, 0, plus the vector v obtained earlier, 1, -7, -10 times t. And we're done. Questions about how this one went? Okay. One more kind of problem to look at. Then we're done. Lines and planes. Get the distance from a point to a plane. I'll draw a picture of a situation. So here's our plane. And here, so here's our point. R0 that sits within the plane. But you want to find the distance. Okay, take my notation here. Right. So here's some point that's outside of the plane. You'll label that E1 that has components x1, y1, z1. And R0 of a point in the plane has components x0, y0, z0. Okay. So, well, I need to explain what I mean by distance from a point to a plane, because yeah, the shortest distance from a point to any other point in the plane. And based on what I talked about some time ago involving projections, you want the best approximation of this point by a point at somewhere in this plane. And that means, and that best approximation okay. At this point, I'll label P2 such that the vector between these points must be orthogonal to the plane. But remember, the plane can be described in terms of a normal vector n that is already known to be orthogonal to every vector in the plane. What that means is this vector here, it must be parallel to the normal vector n. Okay. Now, the magnitude of this is what I'm really after. So this distance d is what we're trying to compute. All right, so it's the length of that vector right there. Now, if I draw this vector, P1 minus R0, so I'm going to call that this vector V1. Okay. Now I formed a right triangle. I have this vector V1, and I have this vector which is at least parallel to n. So then, if I let theta be this angle between V1 and then this vector here, theta is the angle between V1 and n. And all three of those vectors are, all two of these vectors are known, because n, I read off the equation of a plane. V1 comes from these 2 points that are known, because that's the point I'm trying to find the distance to a plane, and that's some given point in the plane. All right. Now, using right triangle trigonometry, D is equal to the magnitude of V1 times the cosine of the angle between V1 and n. Okay. Now, it's not our actual formula for distance, but it's getting us there. So now what I'm going to do is I'm going to multiply and divide by the magnitude of n. Okay.
Starting to look a lot like cross product over magnitude of n.
Not cross product. Close.
Dot product.
Dot product involves a cosine. Cross product magnitude involves a sine.
Yes.
Alright, so this numerator is the dot product of V1 and N. Then we divide by the magnitude of N. Okay. But now,
Are those lines the magnitude of the dot?
well,
The
you mean the
absolute
absolute value is the magnitude.
Okay.
Yeah. I don't know if which notation to use in the homework problems, if you use single bar over double bar, which also means magnitude. Okay. Let's suppose a plane. You get by the generic equation. AX plus BY plus CZ plus D is equal to 0. And I'll refresh your memory that D is equal to minus A X naught minus B Y naught minus C Z naught. But that's the same as minus R0 dot product with N. Okay. So remember V1 is the difference between these 2 points. So this dot product is X minus X naught, X1 minus X naught. X1 minus X naught, Y1 minus Y naught, Z1 minus Z naught, dot product with the vector, the normal vector, which is ABC. Absolute value, and then the magnitude. Oh, I'm sorry. That's vector magnitude.
Yeah,
This is just plain absolute value
okay, that's what I was.
because it's a number. Okay. Then the magnitude of N, that's square root of A squared plus B squared plus C squared. But I can simplify this a bit more. All right, the denominator is done. Okay, because what I have here is this is the same as AX1 plus BX1 plus CX1 minus A X naught plus B Y naught plus the Z naught. If I just write out what this whole thing is. Don't worry, you're suffering will end soon.
Just so long.
But that's D. As I wrote up there. So we have AX1 plus BY1 plus the Z1 plus D. So it turns out you actually don't need to know the coordinates of any point in the plane. You just need the equation of a plane. So what you do is, to get the distance, you take your point that you want the distance to a plane, you plug that into the equation of a plane. It's not in the plane, so it's not going to satisfy it, so it's not going to be 0. But whatever it is, then you effectively normalize it by dividing by the magnitude of N, and that's your distance. Okay. Okay, so now I can do an example, and I'll get out of here. I think if I had a full 35-minute class, I'll be asleep by then. This isn't differential equations. I want to do the existence of D, just prove class be writing in pain. All right. Okay. So, what distance between this point, 4, 5, 6. Okay. And you have a plane. Is x plus y minus 4z plus 15 is equal to 0. Okay. So the normal vector on ABC, read off the equation of a plane, 2, 3, minus 4. So now we can go to the final version of a formula and get your suffering over with. So then we have, you plug in the coordinates of your point of interest into the equation of a plane. So this equation right here, so we have 2, 4 plus 3 times the y coordinate, it's 5, minus 4 times 6, plus 15, over square root of 2 squared, plus 3 squared, plus 4 squared. Okay. So work out all of this. 30, 38, 14. Over square root of 29. So that's the distance. Don't forget the absolute value in the numerator, because when you plug in whatever point into an equation of whatever plane, the result could be positive or negative, but this is distance, so it's got to be positive. In this case, it turned out to be positive anyway, but aware of that. Right. If you have this formula, can also be used to compute the distance between two parallel planes. If you have one point in one of the planes, then you can use this formula to compute the distance from that point of one plane to the other plane, and that's the distance between planes. Okay. Any last questions about lines and planes? Oh God, it seems like them. Don't get on the ball. Okay. All right. I guess we're done. Mercifully so.